the sum of the cubes is a square. Let's say we have 1 cubic plus 2 cubic plus 3 cubic plus dot dot plus n cubic is equal with 1 plus 2 plus 3 plus dot dot plus n, everything square. So before we are proving this statement, this theorem, let's first of all see the right side. And the right side, if we are taking the right side here, so let's say is 1 plus 2 plus 3 plus dot 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 plus n, we already know this is equal with the n times n plus 1 divided by 2. But now, here we have the right side is 1 plus 2 plus 3 plus dot dot plus n square. And if we are squaring this equation, both sides is going to hold. If we are squaring both sides. And now, according to the transitive property, we have a right to write this equation, this original equation here, this statement, 1 cubic plus 2 cubic plus 3 cubic plus dot dot plus n cubic is equal with the n times n plus 1 divided by 2, everything square. And now we are going to prove this by inductive reason, or we are going to prove by induction. So now, first of all, let's take n is equal with 1, and let's see does this equation hold. And if we take in n is equal with 1, here is 1. And in the right side here, I'm plugging n is equal to 1. Whatever I see, I'm plugging 1. 1 plus 1. Everything here divided by 2 is square, but this is a cubic. And this is a 1 cubic is going to be equal. So 1 plus 1 is 2. 2 times 1 is 2. Divided by 2 is what? 1 square. So 1 cubic is equal with 1 square. So it holds. Now we are going to look, does it hold when n is equal with n plus 1? And now, whenever is a n, I'm going to plug in n plus 1. And I'm taking this equation here. And this equation here is going to be 1 cubic. So just let me write the different color. 1 cubic plus 2 cubic plus 3 cubic plus n cubic plus n plus 1 cubic is going to be equal with, now whenever is a n here, I am substituting n plus 1. N plus 1. And here instead of the n, I'm plugging n plus 1. Plus 1 is n plus 2. N plus 2. And everything here divided by 2. And everything is square. Okay, we are here in this situation. But one thing we have. We already know what we have this equation here. Just this part of the equation. 1 cubic plus 2 cubic plus 3 cubic plus n cubic. This was equal with the n plus 1, okay, divided by 2 squared. Just this part here. So because we already see here on the top, we already see 1 plus 2 cubic plus 3 cubic plus dot dot plus n cubic is equal with the n times n plus 1 divided by 2 squared. We already see this part here is equal with n times n plus 1 plus 2 plus square. So instead of this whole these numbers, so here is dot dot plus n. So instead of whole this series here, this part of the series, I'm going to substitute by n times n plus 1 divided by 2 square. And now this equation is going to take this form. N times n plus 1, okay, here is divided by 2 square, plus n plus 1 cubic. So this part here, n plus 1 cubic, is equal, so let me go a little bit further. So this is equal with the right side, and the right side I'm writing in the way how it is. And the right side is n plus 1 times n plus 2, everything here divided by 2, but here is a square. So now we want does this equation hold. But to make a little bit easy, this part I'm going to move in the other side. So everything here I am going to subtract by n times n plus 1 divided by 2 squared. But in other words, this one I'm going to put in the other side, so I'm taking a shortcut, and the sign is going to change here to become a negative, but on the left side is going to remain just n plus 1 cubic, is equal with n plus 1, n plus 2, everything divided by 2. Here is a square plus minus, I'm sorry because it's going to change the sign. I already said that, but for some reason I wrote plus, is a minus. This part here, because we move it in the other side, or we are subtracting everything by n plus 1, and here is going to eliminate, and here is a minus n times n plus 1. Everything here is a square. And now let me make a little bit easy. Okay, I'm extending. Okay, let me make a little bit easier. Let me take a different color. Here is a n plus 1 cubic. It is equal, and if I'm distributing this square here in everything, here is going to be n plus 1 square, n plus 1 square, and here is n plus 2 square, and this is going to be divided by 4. In the other side here is going to be minus n square, and this one n plus 1 square, and divided by 4. And what do we have here? So let's work a little bit with the algebra here. Okay, so the denominator is 4, and here is n plus 1 square, n plus 2 square, minus n square times n plus 1 square. But as you see here, n plus 1 square is a common denominator, and n plus 1, it just is a cubic, so do not forget this one here, is equal with now we are taking n plus 1 square, we are taking as a common factor, and what remains here, n plus 2 square, n plus 2 square minus n square. This is what remains here, and this is here, because n plus 1 is square is a factor, divided by 4. And now let me do some extra step here, and we are almost done. And this is a n plus 1 square, and now n plus 2 square, I'm going to distribute this one here. Okay, here is divided by 4. If we are n plus 2 square, if we are using binomial formula, is going to be n square plus 4n plus 4 minus n square. And as we see here, n square with the n square plus n square minus n square is cancelled, and here remains n plus 1 cubic is going to be equal with n plus 1 square, and here 4n plus 4n remains just 4n plus 4n, 4n plus 4 divided by 4. And because here we have a 4, we can factor this 4 in the front, and if we factor this 4 in the front, what is going to be here is going to be 4 times n plus 1 square times n plus 1, everything here divided by 4. 4 with the 4 simplifies, and n plus 1 cubic is going to be equal to the n plus 1 square times n plus 1. And we already see this is a holds, because both sides are equal and this equation holds. Therefore, we just proved by induction this theorem is true.